So we're now at the last step of proving the Pontryagin duality. We just need to show that the image of this big phi is going to be dense in the double dual group. So first of all, let's start by the following technical lemma. Suppose I have two compactly supported functions as called psi and eta. Then if you do their convolution, then this convolution is going to be the Fourier transform of some B1 function, okay? So to prove this, well, first of all, I have two functions on the G hat. So how about let's convert them back to functions on G by doing the inverse Fourier transform. So I define f of x to be the integral of basically plug in the formula for the inverse Fourier transform. I do the phi x psi of phi d phi, and then I let G to be the inverse Fourier transform for eta. So phi of x eta of phi d phi. All right, so then I get two functions on G. Well, first of all, because your psi and eta, they're just compactly supported functions, so they're nice. So they are certainly in L1. So when you multiply by the Haar measure, you get something in M of G hat. So now when you do the inverse Fourier transform, you get something inside this B function, okay, the B of G, okay? So automatically you have F and G, they're both inside B. So moreover than that, well, we actually want to show that this f and g, they're both L2 functions. So in fact, when we multiply them, we'll get something in L1, and that's going to be the function h, all right? So let's first of all show that f and g are L2. So to show they're L2, I just need to show that if I do the inner product with another L2 function, then I get something that's actually bounded, okay? So by the Riesz representation, the L2 is a Hilbert space. So I know f and g are both in L2. So let's just take for every k inside the L2 of g, and because I need to do some Fourier transform, so let's just say inside L2 intersect L1, so that's a dense subset. So if I consider the integral, let's just say f multiplied by k dx, so their inner product. Well, let's just write out by definition, this f is an integral of phi x is the inverse Fourier transform of the psi, so psi of phi, and then I also have a kx, the whole thing conjugate. I have two integral, one is dx and one is d phi, okay, one on g and one on g hat. All right, so now let's reorganize this integral a little bit. So let's move the psi of phi outside, okay, and I do the integral on x first. So I have a phi x, and I have a kx bar, but let's put a bar here and I put a conjugate over here. And then I have a dx and a d phi. So the reason I put a conjugate outside is that now I have an integral of k against the phi conjugate, which is just the Fourier transform of k. So this one is going to be equals to the integral of psi of phi. And I do the Fourier transform, evaluate at phi, and then I do the conjugate d phi. And so once we have that, well, I know this psi is going to be in compactly supported, so that's certainly in L2. While k by Plancherel, I know k hat is also in L2 of the G hat. So this is the inner product of the L2 function psi with the L2 function k hat. So this one by Cauchy-Schwarz, that's going to be less than equals to the L2 norm of psi multiplied by, say, psi, L2 norm to the half, multiplied by the L2 norm of k hat to the half, which is just the L2 norm of k. Okay, so this is just by the Plancherel theorem, that's the L2 norm of k. But in any case, this whole thing, this inner product of f with k is going to be bounded by the L2 norm of k to the half multiplied by some other constant. So this just shows that the f is also in L2. So f is inside L2 of G, and you do the similar thing, that G is also inside L2 of G. So now we observe that if you have two L2 functions and you now multiply them, then you have something inside L1. So let's just take their pointwise product. So that's going to be in L1 of G. And what it does, if you evaluate at the point x, well, let's just write this integral. So first of all, this is, you put the two integral together. So what you have is that on one hand, the f is the integral of some, say, phi of x, and then you have psi of phi. And the other one is essentially just equals to some phi of, you probably don't want a phi, let's say use a cosine. Let's say cosine of x, and you have an eta of cosine, and then this is the integral over two copies of the g hat. Okay, so one is d phi and the other is d cosine. All right. So now let's reorganize this integral. I write it this way. So this is essentially doing, I have a phi times the other character is cosine. And then I also have a psi of the phi, and I have also an eta of the cosine, okay? So let's pretend this is an integral over phi first. So let's maybe move all the cosine outside. Okay, so let's do the following. Let's keep one cosine here, and then let's move the, this is the d phi. And then I do the eta of cosine outside. And the good thing about this d phi is that the d phi is a hard measure on the g hat. All right, so by last translation, I can just translate this cosine inside. Okay, so I pretend this is a translation of this my variable phi by a cosine. Okay, so this one is just going to be the double integral of well, cosine just disappeared, but the sine of phi will have a cosine inverse. Okay, and then I have a d phi, and then this whole thing I multiply by eta of cosine, d cosine. And now let's see what we have, okay? So if you just rewrite it this way, so let me just move everything back. So I have a double integral again. I have a phi of x. And now I want to do the other way, okay? So let's do the d cosine first. So I have a, move the integral here. So I have an integral of the psi function evaluated at phi cosine inverse, and then I multiply by eta of the cosine and d cosine, okay? The whole thing d phi. And this one is just the convolution, okay? It's the convolution of the psi function with the eta function, okay? So you see this d cosine, you have cosine inverse and cosine, they cancel out. So this one becomes the phi convolute with eta evaluate at phi, okay? So this function is now is just equals to the phi x psi eta convolution d phi, okay? And let's give this function a name. Let's call it h of x, okay? So this h of x we know is going to be, well, kind of the inverse Fourier transform of this convolution of the psi and eta. So because of that, this h is inside, well, first of all, this cosine and eta, they're both compactly supported. So this h is certainly inside b of g as well. And h as a product of f and g, that's inside L1. So there's also f and g both in L2, so their product is in L1. So this h is certainly inside B1, okay? So h is inside B1. And now because it's inside B1, then I can apply the Fourier transform. And this h hat, or the inverse Fourier transform, basically tells you the h hat is where it came from, okay? So this is essentially just the Fourier transform. So psi convolute with eta is just the h hat. All right, so now we're ready to prove the last bit of this theorem. I want to show that the image of phi of g under the g double hat is extends. So let's suppose I have something that's outside this range. Let's say phi hat is inside g double hat, and suppose that's not inside the image of this big phi, okay? So I want to show that this phi hat is going to be in the closure, okay? So now because I have, we just showed from last video that I have something that's closed. So in other words, I can have there exists some V open neighborhood of the identity. Let's just take this so that it's symmetric. So that I have this phi hat times V is disjoint from the phi of G. Okay, so phi of G that's going to be equals to the empty. Okay, so it's disjoint. So now I have this V, so I can take something that's supported on this V. I should say this should be on E hat, so V is open inside the G double hat. So I can find some, let's say, psi and eta. So psi and eta, they're inside compactly supported function on the double hat, so that I can have the support of this phi. Psi is inside, let's say, phi hat translated by V, and then I let the support of the eta to be contained in V, so that when I do their convolution, it's going to be supported on their product, okay, on the product of these two support, which again is disjoint from the phi of G, the image of phi. All right, so now I have that the support of these, not phi, oops, I should have psi convolute with eta. That's going to be contained in the product of these two supports. So I have a phi hat times V times another V. So this is disjoint from G, phi of G. Okay, so it's going to be disjoint from phi of G. So by the lemma we just showed, now I convolute two things that are compactly supported on the G double hat. You think about that as the dual of the G hat. So there I can find some H inside the B1 function of the G hat now, so that this is equals to the H hat. Okay, so H hat is equals to psi convolute with eta. Okay, and so by our choice, I have the support of this H. That's going to be disjoint from support of the H hat is going to be disjoint from the image. Okay, so disjoint from phi of G. Okay, so because of that, well, if I evaluate a H hat at a point, let's say X hat, well, because the support is not there, so it's going to be equal to 0. But on the other hand, what it does is basically the integral. So this is the Fourier transform of H. So this is H of phi, and then I do the X hat at this phi, and then I do the conjugate d phi. So that's the definition of the Fourier transform of H. But X hat is the evaluation at X. So this is just equals to H of phi. I have a phi of X conjugate, and then I do the d phi, and that's going to be equal to 0. Well, so now what happens is, well, if you just take, because this is for every X, you have that if I do the integral of phi X, and then I do the H of phi d phi, that's just going to be equal to 0. Okay, this is for all X inside G. So what happens is, well, if you want to integrate for each of these X, when you integrate against these H d phi, which you treat it as, because H is inside L1, so you treat it as a measure inside M of G hat, you always get something 0. One way you think about the pointwise, another way is you think about the inverse Fourier transform of this measure is equal to 0. So because this measure is equal to 0, we show the inverse Fourier transform is injective. So this just implies the H d phi that's going to be equal to 0. So in other words, H has to be 0. Okay, so H is equal to 0, and H is equal to 0, so H hat is also equal to 0. Well, but H hat is equal to 0, that's just equals to the convolution of your two functions. Okay, so this is psi convoluted with eta. So that's going to be impossible because you pick some non-zero function. You can always pick the psi and eta to be strictly positive, so their convolution is not going to be 0, at least not on their support. Okay, so this is a contradiction. Okay. All right, so now we finished the last bit of this proof.